Welcome everyone online. Thank you for joining this afternoon, Central European time. And today's webinar will focus on hybrid AI with a demystification theme to it. We will be focusing specifically on the oil and gas industry, as well as process manufacturing industries at large that are adjacent. Before we go in, let us walk you through a little bit of the housekeeping for today's session. So we have planned about a 40-minute worth of presentation for you today, as well as a 10-minute session on open questions and answers at the very end. When you do get questions, as we are broadcasting at scale today, we cannot unfortunately interrupt the flow with questions in the presentation itself. So please just post those into the questions box and we will answer those at the end of today's webinar. When we have more questions than we have time for in the open session, we have more than available time to continue running over with those of you on the call at that time. Also, a link to the presentation video will be shared with all participants after the session, which is another way of saying that we are recording today's session. And as always, you can reach out directly to us or visit cognite.com for more information afterwards or at your own discretion. So your host today, my name is Petteri Vainikka. I'm the Vice President of Product Marketing at Cognite, and I'm joined today by my esteemed colleague Gunnar Staff, who will be carrying the payload of today's webinar session. Let me, before we give the floor to Gunnar, just very quickly run you through the agenda today. So I will be your host for about 7 minutes worth of a quick introduction to Cognite. And then we will jump into today's brief, which is the short but very instructive history of machine learning and deep learning failure in oil and gas. Then we will move into feature engineering, giving a roadmap to physics-guided machine learning. We will then feature a demo of hybrid AI applications, focusing on forecasting, root cause analysis, and prescriptive action systems. And then we'll discuss how we can transfer the lessons from oil and gas to all other industries that produce goods such as cement, paint, or fish oil for that matter. So without further ado, very quickly on Cognite, we are the fastest growing technology company in Scandinavia, employing currently around 400 employees and growing very fast. And our offices are present globally. So we have a footprint from Tokyo all the way to the United States with a headquarter office in Oslo, Norway. And our customer verticals today are focused around oil and gas, manufacturing and after-sales services markets, power and utilities, as well as shipping. So very briefly, why and at what stage do customers typically reach out to Cognite? We very much focus on the beyond proof of concept phase of our customer market. And our product offering consists, broadly speaking, of three different offerings. One is our platform product, Cognite Data Fusion, which is a data operations for industry platform that makes all industrial data accessible, understandable, and useful, both for data scientists as well as developers. We also offer a suite of Cognite industry applications that are packaged, customizable applications that can be decomposed and recomposed by our customers to fit their special requirements. And these are focusing on production optimization, smart maintenance, digital worker, as well as sustainability. And last but not least, we also have a team focusing on hybrid AI solutions for our customers that works closely with our customers and our customers' preferred data science partners around the implementation of what is predominantly hybrid AI application development initiatives, as well as the scaling of those, of course. So very quickly on Cognite Data Fusion, we are, again, an industrial data operations platform focusing on digital transformation. A lot of our customers picture their digital transformation initiative sort of evolving around a digital twin solution. And just to give a very high-level introduction into how we at Cognite think about digital twins, we look at them as consisting of three broad layers of technology capabilities. These could be separate products or they could be synthesized into a class of fewer products. So we have industrial data management with a specific focus of handling time series data as well as non-structured data that is very, very unique to industrial operations. Then there is the data science layer or the advanced analytics layer, which is equally consisting of physics simulations. That is a very proven methodology within processing industries and has been applied successfully for decades. And last but not least, we have the application development layer, where the emphasis today and going forward is very much on reusability and efficiency through the delivery of low-code frameworks and the equivalents. And then coming to where we are and what the session for today will focus on. So we have two sides of the equation. So there's the backend side, which is Cognite Data Fusion, which is the platform that actually enables the rapid application development of advanced analytics, including hybrid AI applications. And then we have the front end side of the equation. Most of the time when people look at applications, we tend to look at the front ends. Today, we will discuss with you how the backend and the front end work together. And tools are, of course, critical and crucial. There is commonly one backend, or you may have multiple backends as well. The plurality of the front ends is, of course, an order of magnitude higher. And just to give you, again, a summary and a slight introduction, today we will very much be focusing on what the backend looks like for hybrid AI. That is, it's a very unique combination of machine learning with physics, first principle simulations, that is uniquely applied to industrial challenges. And we will walk you through a series of these today. As an overview and an introduction, these are some of the advanced analytics customer success stories that have been solved with the use of Cognite Data Fusion. We will touch upon a handful of these today, but the main story today will be how do you actually get to this? So how do you get to advanced hybrid analytics application delivery and operationalizing at scale? And what can we learn from oil and gas that we can apply to all other verticals alike? With this introduction, I hand over to my esteemed colleague, Gunnar Staff. Take it away, Gunnar.
So thank you. So now we'll dive into the slightly more technical part of this presentation. And this is quite apparent from the abrupt change of quality of the slides. Now we go from the nice marketing slides to the more engineer style of slides. So first, we know that machine learning has been immensely successful in many areas, like fraud detection, image recognition, personal newsfeed, targeted marketing, and also games. However, it has not been equally successful in oil and gas production. And this is despite the really high value potential. So the question is, why? There are several big differences between the classical machine learning applications and oil and gas application. And it's important to understand this before we understand how we can solve the problem. So first, there are often no alternative approaches to classical problems. So you don't find a mathematical equation for how you can stack the groceries in a store such that people buy more. However, in oil and gas, you're competing against highly successful physics models. This has been used for decades, it is validated, and it's trusted by the end user. Large error is not usually a big problem for classical machine learning models. So if you present the wrong ad, it is not a catastrophe. However, if you give a wrong advice to the operator, you may actually result in a big accident. So large error can have serious consequences in the oil and gas industry. There's an enormous amount of training data for many classical applications. For instance, you can find millions and millions of pictures you can use to train a model. There aren't that many data for oil and gas. So often you believe you have a lot of data because you have 20 years of sensor data. However, that is not the same thing as a lot of data. So we'll come back to that later. Some of the problems for classical machine learning applications, they are noiseless. So there is no noise in the data. However, for sensor data, you usually have a lot of noise and you have drift. So you have both high variance and bias in the data. So I will present a very simple illustration of some of the challenges. So this is an example of the underlying physics. And as you can see, this is a classical nonlinear behavior. This is very common in oil and gas. As we said, the problem is that we have noise in the data, and we also see that it's a huge bias in the distribution of the data. There are multiple reasons for this. Typically, we know that the condition of the field is changing. So which condition you're operating under changes, so the old history is not necessarily relevant. Due to the low number of data points in some areas, we are predicting really wrong for the right side of this function. This is the area we want to operate because we're trying to optimize, we're trying to operate in the area we haven't been able to operate before. And this is an area where we now have a huge error, and that is a big problem. So these are some of the challenges we need to handle. So long history is not the same as a lot of training data. The reason is that often the models require stable production conditions. So transient conditions will not be covered in this presentation. So what a stable condition means? First, it means that you don't have any operational change. Second is that every initial transient has to die out. So even though you have you change your settings, you will have a transient in the system. Sometimes this transient is short, sometimes it's really long. Also, if you end up in an unstable situation, you're in a pseudo-stable situation, you need to have this situation for quite a long time so you can average over a certain period. If not, it will not be representative. If you add all this together, you will end up with not that much training data as you would believe. Also, we know the conditions are changing during time. So the reservoir pressure is declining, you are adding wells, you're abandoning wells, and you're modifying the plant. So again, you have less data than you would believe. And the last and most important, production optimization, is about pushing the envelope. So we're trying to operate in a region where we haven't operated before, meaning that you have little to none data in this region. So let's compare the physics simulator and machine learning. It's important to understand how we can combine these two methods. So first, a physics simulator can predict without any access to the historical data, or at least they claim they can. So it means that you can actually predict from first oil. Machine learning models require a lot of training data for relevant situation. The physics simulator have been tested and tried out. It's trusted by the industry. Machine learning models are still fairly unproven. It's hard to interpret the logic behind it. It's black box. It makes it harder for the engineer to trust it. And the engineers really want to understand what's going on in order to validate it and trust it. The problem with physics simulators is that it's hard and sometimes impossible to derive mathematical models for any kind of problem. Machine learning models, in theory, can work on any kind of problem. In reality, it's not as simple as that, but it is not that sensitive for if it's possible to derive a mathematical model or not. Also, a physics simulator has some hard requirements. You need a certain set of boundary conditions. You need a description of geometry, you need the fluid and materials, etc. You don't need this for a machine learning model. However, it will influence the accuracy. A physics simulator can predict outside the range of the existing data. This is more questionable for machine learning models. Commercial simulators are often very expensive and very computer intensive. However, once you have trained the machine learning model, it's usually quite cost effective to run. It means that it is possible to run it on real-time streaming data. Physics simulator can also predict into the future, and by that I mean a transient situation. This is more questionable for a machine learning model. It is possible, but we'll not touch upon that in this presentation. Also, a physics simulator can predict any value for any position. However, a machine learning model can only predict for the data where it is trained. So we see that there is a lot of pros and cons with the different methods, and what we want to do is to combine them with what we call the hybrid AI model. So what we want to do now is to try to explain what is really hybrid model. You are combining two big buzzwords, and the question is, will you get something that is even better? And we will show that it is actually not as mysterious as it may sound. So first, just a simple reminder. So in this presentation, we'll only look at regression models. So what is machine learning really? So the goal is to predict something. In this situation, I have an example of what is the amount of liquid in your pipeline. So we want to predict that for a certain production condition. We have some data. That's the measurement of the liquid content for a certain set of production condition. So training a machine learning model on that data such that we can predict for, in theory, any kind of a production condition. Mathematical modeling is a lot more complex. So you can say we have two extreme categories. So one's called the first principle modeling. It's really rigorous, really complex. We know, for instance, that you can derive conservation equations like conservation of mass, momentum, energy, and volume. These are the basis for a lot of the commercial physics simulators. In the other end, you have what's called empirical modeling. This is much simpler, but more uncertain. And the extreme version is basically a curve fit to data. And now we're starting to see some similarities between classical machine learning and mathematical modeling. So in order to understand this better and to show that it's not as complicated, I will use a simple example from a mathematical modeling to show how these techniques can be used in machine learning. So we want to create an empirical model for the accumulation of liquid in a gas condensate pipeline. This example is borrowed from a paper from a former colleague of mine, Biberg. So we have data from experiments. The situation is we would like to see how much liquid can we push into the pipeline for a given gas rate before we start to accumulate a lot of liquid. This is very relevant for all gas condensate pipelines in the world. So we have data for different gas rate, different pipe diameters, inclinations, and different densities. So in principle, we have 5 different input features, and we have 1 parameter we need to predict. So to the right, you see some of the experimental data. So the lines are the result from a physics simulator, and the points are the measurements. So you can see that the simulator is quite accurate. We see some noise in the data around the predictions. So every line represents a series of experiments where a single parameter is changed. And remember, we have 5 parameters, so it's a quite complex situation. And as you can see, the behavior is really nonlinear. So how can we create a model that predicts these data? So imagine if the behavior is complex, you need several points in order to describe it. So if you, for instance, need 10 points per spatial dimension, you actually need 100,000 different experiments, which is not going to happen. So the challenge is that the data requirement grows exponentially with the number of input parameters. Then we go back to what we learned in the university. And then we took mathematical modeling, of course. And then we learned about something called dimensional analysis. And from fluid mechanics, we learned about the dimensionless numbers like the Froude numbers. So what we're trying to do now is to change the parameters from the experiments to different parameters, which is feature engineering, such that we can describe the results more easily. And to the right, you see that by doing this feature engineering, or creating these parameters, we actually collapse all the data. And note here, we have more data than on the previous plot. So all the data line up fairly well. So it's almost a linear correlation. So there's some deviation, but it's very close to linear. So what we did was to collapse this really complex behavior into something that's much more linear. And it means that if we're going to describe this behavior, we don't need that much data. So we went from 5 to 1 feature, meaning that we actually, if we assume 10 data points per dimension, we reduce the requirement for data by a factor of 10,000, which is quite significant. Now we can actually choose how are we going to fit this data. Are we going to choose the function? That's what you typically do in mathematical modeling. Or are you going to use a machine learning model to predict that result. So what's the learning from this? The learning is that when we do feature engineering in the right way, we can reduce the number of dimensions. So this significantly reduce the data requirement, which is important since we already said that we do have limited amount of data available. The behavior of the problem we're trying to predict is now much simpler and much smoother. So it's easier for the machine learning model to describe this behavior compared to the more complex. So we can see that for simple problems, there's a lot of similarities between mathematical modeling and machine learning. If you're an engineer, you will probably say, but I trust the sensors. I don't trust this feature engineering. That looks really suspicious. So the question is feature engineering really a radical approach? And the answer is no, it is not. So we have to remember that we don't measure the values that is reported from the sensors, almost never. So for instance, a flow meter does not measure the flow. It can, for instance, measure the pressure drop, and you know a lot about the geometry, etc. And then you use mathematical models to back calculate what is the flow rate. So already you are in a way using feature engineering when you're using sensor data. So what we are doing is really to extend this work. So we're putting in more information here. And one of the things you can do with feature engineering is to add information that is not part of the sensors. One example is to add the information of the fluid. So we can add the fluid characterization. We can combine that with pressure and temperature sensors and with the laws of thermodynamics. And then we can compute additional values that is useful for the feature engineering. So there's a nice quote from Wikipedia saying that feature engineering is a process of using domain knowledge of the data to create features that actually makes machine learning algorithms work. I will now show some examples where we have used hybrid AI, or what I like to call physics-guided machine learning, to solve problems for oil and gas. So I will, in this presentation, only show use cases from Aker BP, since we have an agreement with Aker BP to show more details. So the use cases are developed in collaboration between Aker BP, Cognite, and different partners. The first is a quite complex use case. So this is about a well where the reservoir sometimes collapses very close to the inflow zone. It creates a suspension of the particles from the reservoir with the oil. It enters the well bore and it partially or completely blocks the well. This is a big problem for the operator. They may lose the production, which costs a lot, and they have to do mitigation. The engineers need an alert system that can notify them that this event is ongoing, such that they can try to mitigate before it completely blocks the well. So the well is a gas lifted well. So it is described by 7 different sensors. So if you look to the to the left, you will see all the different sensors. This shows a choke influx event, or an event where we had this near well collapse. It's really hard from that set of sensors to identify what's going on. What we did was to use a physics simulator to back calculate. So we're saying the change is in the inflow zone. Then we can use the sensor values and using the physics simulator to back calculate what is the actual change in the inflow zone. Then we get a single parameter, a single feature to the machine learning model instead of 7 sensors. This behavior is much simpler to run anomaly detection on for a machine learning model. So this is an example of a hybrid model where we use the physics simulator to reduce the complexity of the input space from 7 to 1 input parameter, significantly reducing the amount of training data. The second one is actually in a way similar. This is for a heat exchanger. So the heat exchanger was fouling. It was not detected it came to a point where the efficiency was so low that the production had to be stopped. It was a huge loss. The first approach from a different company was to try a pure machine learning model that did not work. Then another company in process came in and did a classical hybrid solution. So they did something similar based on the sensor values and the description of the heat exchanger. They back calculated what is the efficiency of the heat exchanger, which basically is what is the fouling factor. Then again, you have a single parameter, and then you can use machine learning to predict what is affecting the fouling rate. When will the fouling be so severe that you need to do maintenance? So this can be used to plan when you actually need to do maintenance to both prevent shutdown, but also when it comes to efficiency. Now we'll switch to a live version. So this is a more complex use case. So this is about the separation process on one of the assets. So they're producing a lot of water. The water is dumped into the sea. In order to do that, you need to clean out all the oil. So there's a strict limit on the amount of oil you're allowed to have in the water before it's dumped. Sometimes it's hard to meet this requirement. It is also challenging to understand where in the process do you have a problem, because this changes based on operational condition. So what we did was to set up this automatic anomaly detection or automatic root cause analysis system, which could point to the different stages in the separation or production where you actually had the problem. So here we see a schematic of the system. So we have the well templates to the left, we have the main separators, we have the hydrocyclones, and at the end we have the sample point for the outlet of the water. We use the machine learning model to back calculate what is the influence of the different components. Then we started to add physics because we know a lot about this problem. So it's not possible to compute this using pure physics simulator. However, we can add a lot of our understanding of this problem. So we know, for instance, what creates emulsions. We know that unstable flow create emulsions. We know that valves or chokes create emulsions. We know how much emulsions is generated or how it scales with a pressure drop across the choke. We know that pumps create emulsions. We know a lot about the separation. We know that the residency time in the separator affects this. We can back calculate the residency time. We know that we can compute the terminal velocity of the droplets based on the size, meaning that if you combine that with the residency time, you actually have a clear description of the efficiency of the separation process. This is influenced by the fluid properties, of course. This is computed on the fly. So we have the pressure, temperature, we have the different fluids, we can mix that and find the fluid properties. This improved the prediction of the model quite significantly. So this is compared against the measurements. So initially it was only spot samples, and then you had the added value of this use case. So it means that then you had a soft sensor that continuously predicted the efficiency of the separation. So until that point, they really didn't know if they produced with too high emulsion before they had the result of the spot samples. With a soft sensor, you will be able to see that on an earlier stage, and you can do mitigating actions right away. A classical way of combining physics simulator and machine learning is what's often called a proxy model. So in this situation, we needed to compute the maximum capacity of a PSV system. This is a safety critical system, and it's absolutely critical that you predict correctly, or at least if you are predicting wrong, you have to be on the conservative side. In this situation, there is no data available, basically because you have never produced so much that you blew up the separator. So what we did was to compute the capacity of the PSV system using a simulator. And in theory, we could have run this simulator in real time, and every time the production condition changed, you could use the simulator to compute what's the maximum capacity. However, that is quite computer intensive because it's a complicated simulation. And also know that simulators are sometimes they crash. They are slow. So what we did was to pre-run all possible scenarios. So we created a big set of training data. Then we fitted a machine learning model on this data. This model can interpolate for the given production condition. And this is the basis for the model that runs live and continuously computes how far are you away from the maximum capacity on your PSV system at any given point in time. So why is this useful? Well, first, the machine learning model, is much faster than the physics simulator. It is also much more robust. So when you pre-run a simulator, you can use a lot of manual tuning to make it run. You cannot do that when you run it automatically. It is also much cheaper because if you have to run a simulator real time, you need to have a sufficient amount of licenses. And the licenses are usually very, very expensive. So now the question is, how can we transfer the learnings from oil and gas to other industries? It's important to remember that other industries, the behavior is also governed by the physics or the chemistry, similar to what you have in petroleum engineering. We also have a lot of the same equipment. You have pipes, there are fluids inside the pipes, there's valves, heat exchanger, filters, boilers, pumps, etc. So any model that works on these types of equipment from oil and gas will also work on a similar equipment for other industry. And the same technique, by trying to change the system from a complex system to a simpler system by using physics, it's also applicable to these industries. So at the bottom, I've shown some of the industries that we are talking to. One interesting is cement, as my colleague mentioned earlier. So an interesting feature about the cement industry is that they are really strict on the quality of the cement. The problem is that it takes about 4 to 5 weeks before you have the result of the quality check. Then the product is shipped out to the market already. It means that then you actually have to get back the product you shipped. If you can set up a soft sensor, like we showed that we did in the separation use case, then you can actually give an indication to the producer if the quality of the cement that is produced is questionable. This will allow them to delay the shipment of the product until they have a verification if the quality is high enough or if it needs to be discarded. Paper production is also a really complex production system. It really requires a lot of energy. There's a lot of optimization potentials there. And also, my colleague talked about fish oil, but I think most people will agree that brewery is more interesting. So it's a very popular project to work on, a lot of nice field trips, but it's actually very similar to oil and gas. You have a lot of fluids, there's chemical reactions, you get multi-phase, etc. There's a lot of transfer of knowledge from oil and gas into these industries.
Thank you, Gunnar, and let's move into the questions from the audience. First of all, thank you everyone for joining today, and now we are onto the live Q&A. We do encourage you to write your questions into the questions box as we move forward. So I'll just actually kind of start from the bottom of the stack on the questions here. There's a question from the audience on, like, what are the prerequisites for doing hybrid AI at scale, given that some of the examples showcased here tend at least look pretty sort of specific and discrete, and can one implement those in a Like, what does it really take to implement one, and what is the difference of implementing one versus implementing a fleet-wide deployment scale?
So I think there's a lot of prerequisites. So one is that you actually have the understanding of the problem. You have this in oil and gas industry, so you have a lot of engineers that actually do understand the problem. So when you collaborate with them, you get the domain understanding you need in order to do this feature engineering. You also need access to the tools. So some of these models are quite simple. You can implement them yourself. Sometimes you need a quite complicated physics simulator, and then you need access to this simulator. So in some situation, we run it on-prem, but it's very useful to be able to run this as a service. So we're talking to a lot of software vendors, and they are working on providing their simulators as a service. And it means that you can run a lot of simulations on demand. So your development is not depending on the internal IT getting access to infrastructure, buying more licenses, and setting up the system. You can very quickly and very easily connect to the simulators at scale.
Thank you. Jumping to the next question. What do you envision will be the accuracy of these hybrid models? Are we talking about plus minus 5%, or what kind of a magnitude are we talking about here?
That is very, very dependent on the problem. So of course it depends on how complex is the problem you're trying to predict. But there's the accuracy of the sensors. So there are of course situations where you can get below plus minus 5%. There are also other situations where the accuracy may be a lot higher. I would say, for instance, if you look at single phase flow, a lot of situations can be way below plus minus 5%. If you're trying to predict the rates on a well with machine learning, it's really, for a multi-phase situation, it's really hard to get below plus minus 5%. So it's very problem dependent.
Then, do we really need to embed physics into the machine learning models? I mean, the strengths of ML model is that they can find the correlation or the correct behavior without requiring any domain knowledge. Adding physics increase the complexity of the development quite considerably. So how do you overcome this increase in development complexity, and is it really worth the effort?
So I think you have to look at the benefits. So if you had an infinite amount of perfect training data, we know that in theory, a machine learning model can predict almost any kind of function. However, we do not have an infinite amount of training data. There's also a lot of noise in the data. We also know that we sometimes need to predict outside the area where we have training data. This puts a lot of requirement on the model. So as I showed in the first example, if we can do this feature engineering, we can make the problem smoother, simpler, and that will give a more robust model that can predict with more confidence outside the area where we have training data. And it can also be more accurate for a smaller amount of training data, which is the most common situation.
Good. Then on to the next one. Which simulators do you at Cognite have the most experience in, and how do you sort of look at the evolution and development of the simulator space itself?
We have used a lot of the process simulators, and we have used a lot of the flowline, well and flowline simulators. So we see a development now in the direction of as a service, which is very useful. So it has been a desktop engineer tool. Now it is a tool that you can automate and run from a script, so a service to service kind of setup. We also see that some of the simulators, they acknowledge that you cannot solve everything using a simulator. So they also see the need to combine it with machine learning models.
Good, and then the final question for today. There's a lot of excitement around deep learning these days, and given that deep learning requires even more training data. One would argue order of magnitude more than conventional machine learning models or more simplistic ML models. Do you see a fit for purpose of proper deep learning methods in oil and gas, for example, or is the industry at large gravitating back towards the physics embedded machine learning just to overcome the basic deficiencies of ML itself?
So deep learning to me is only way of trying to fit a complex function. You need a lot of data in order to train a really deep neural network. So if you don't have that data, it will usually not work at all. So very often you can get better results with a simpler machine learning model. We also see that when you do the feature engineering, you reduce the complexity of the problem you're trying to predict. So it means that you also reduce the need for the flexibility you have in a really deep neural network to predict really complex behavior. So I would say that feature engineering and hybrid AI reduces the need for these large neural networks.
Thank you very much. We are almost up on the time that we have allocated today. We have also covered all the questions that we have from the audience. So if anyone has a final question, we can take that in the last remaining minutes. If not, once again, a sincere thank you from everyone at Cognite for joining us today. And please do look out for upcoming webinar content from Cognite in future. Next week, we will be zooming in on how data operations unlocks true industrial transformation with a deep dive with Trygve Karpe into data operations for industry specifically. And please do also check out 2 reports on cognite.com, one by Gartner and another one by the esteemed analyst community Forrester. So with this, thank you very much for joining us today, and we look forward to seeing you again shortly. Thank you.